Hi y'all, today we're going to talk about the truth table method, which is a method for showing whether or not an argument in propositional logic is valid or invalid. So what we're going to do is sort of go through the basics and get to a point where you should be able to do these for pretty much any level of difficulty. All right, to start, we're going to first say, well, what is the truth table method? And you have to start with just sort of what is a truth table. So a truth table is a table that shows the value of each sentence under consideration in every possible world. So you have sort of a set of sentences in propositional logic. You put them into this table and you calculate what the value of that sentence is going to be in each sort of possible combination of truth and falsehood for the component parts. So remember that the value of a sentence is dependent on the values of the atomic sentences. So the P's and the Q's and the R's and the S's and so on and so forth. So what we say then is, well, if those sentences constitute an argument, right? So if some of those sentences are premises and the other is a conclusion, then we'll be able to tell whether or not it's possible to have all true premises and a false conclusion. And that's going to be important for determining whether or not the argument is valid. So let's look at a truth table. So here is a fairly sort of simple 4-line truth table or 4-row truth table. And we have 3 sentences. We have P arrow Q, not P and not Q. Those are the things, if you look on the top row there on the right, and then on the left in the little black box, what we have is sort of the possible combinations of true and false for our components. So with these 3 sentences, the sentence letters that appear are P and Q. So there's only 2 sentence letters. And so what that means is that there are 4 possible combinations of truth and falsehoods for those P's and Q's. So in row 1, you've got them both being true. In row 2, you have P is Q and true is false. Row 3, P is false and Q is true. And then row 4, they're both false. So what this stuff on the left tells you is essentially kind of what the values are and sort of what you would need to sort of substitute in for sort of P's and Q's in each row in order to sort of calculate the value. So for instance, in row 1, if you're looking at this first sentence here, P arrow Q, then you would substitute true for P and true for Q in order to figure out what the value is. Similarly, you would substitute true here, and you would substitute true here. So that tells you kind of what you need to do in order to do the calculation. And then you do that for sort of each row, and that will allow you to sort of calculate the value of each sentence in each possible sort of combination. So you're going to get true arrow true, true arrow false, true arrow true, and excuse me, false arrow true, and false arrow false for the first sentence, and then you'll have not true, not true, not false for the second sentence, and then not true, not false, not true, not false for the third sentence. So that's just we haven't calculated anything yet. I've just done the substitution to make it kind of clear what's going on. But once you do, what you need to do is calculate the value. So the first sentence here, the value of true arrow true is true. We're using the arrow rule here, so the arrow rule is only false when it's true arrow false, and that happens here, but it doesn't happen anywhere else. So the final values are going to look like this. So true, false, true, true. And then here we got to do our negations, so not trues turn into falses, and not falses turn into trues, and likewise over here, not trues turn into falses, not falses turn into trues. So that is a completed truth table. That is a truth table that shows the value of each sentence in each possible combination of true and false for the component sort of sentences. So those red columns then are sort of what we're looking at. So as I mentioned, then we're going to be able to tell whether, excuse me, if we consider this to be an argument, if we understand these first two sentences as premises, and this last sentence as the conclusion of an argument, then we can tell whether or not it's possible for the premises to be true and the conclusion to be false. So in this case, it is possible. There is a situation in which you get all true premises, but still end up with a false conclusion, right? So the premises can be true, but the conclusion is still false. So if this is possible, what that means is the argument is invalid. That the existence of one of these rows with all true premises and a false conclusion means the argument is invalid. So on the other hand, if you fill out a truth table and you find out that it's not possible, right, that you fill out the truth table and you find that the row does not exist, then that means the argument is valid. So I just want to give you an example of kind of what that would look like. So here is almost the same argument. It's the same sentences, but the only difference here is we've swapped the second sentence with the third sentence. So if we call the second sentence the conclusion and the third sentence a premise, you're going to see that it's not possible to have all true premises and a false conclusion, right? So the table will still be the same for the most part. So this sentence will have these values. So again, over here on the left, if you look, that hasn't changed any. But not Q has moved over here. So false, true is over here now. And not P is now the conclusion. So false, false, true, true. And now you'll see that we never get a situation where we have all true premises and a false conclusion. In fact, the only time we have all true premises is down here in line 4, and everything is true. So it's just never the case that you get all true premises and a false conclusion. Every time you get all true premises, you get a true conclusion. So that means it's not possible, right? If you look again at the thing on the left here, this spells out everything that's possible, right? There's no other possible combination of P and Q with true and false that exists. So it's impossible to have true premises and a false conclusion, and what that means is that the argument is valid. It's not possible to have all true premises and a false conclusion. And if you may have noticed that this argument is modus tollens. Modus tollens, as we discussed in chapter 3, is a valid argument. So here is a demonstration that yes, indeed, modus tollens is valid. Okay, so we're going to continue with some more examples here of how to do this sort of method, just to get you used to filling these things out and then looking for the thing that will sort of indicate invalidity or validity. So remember, a row with all true premises and a false conclusion is an invalid argument, and if that row does not exist, then the argument is valid. So you have to, fill it out and see if such a row exists. So we're going to continue with arguments that only have two sentence letters, so there's only going to be 4 possibilities, but we'll do things that are a little bit more sort of complicated. So here is, again, another argument. So we're going to fill this out, but I just want to show you here that we're going to, the sentences in the middle here are going to be our premises, and the sentence on the right is going to be the conclusion, and on the left is the box that tells us the possibilities. So remember that this is not part of the argument over here. Just these two things. This just tells us what to sort of substitute. So when we do our sort of calculations, we're going to go through and, looking to the left here, we'll see what the value of everything is going to be. So this is going to be, not true or true. This is going to be not true and not true. And this is just going to be true, arrow, true, and so on and so forth. I won't go through and do all of these, but just to give you a sense of what's going on here. Row 2 would look like this: not true or false, not true and not false, and then this would be sort of true, arrow, false. So again, what we're looking for is a situation where you have all true premises and a false conclusion. So you still got to do the calculations here. So I just sort of talk you through this, the order of operations here. So no parentheses to worry about, but you do have a situation where you have a negation and a binary connective. So just remember that the negations need to go first here, because the negation only covers the immediate letter next to it. So this not true is going to become a false. So we're going to have false or true, which requires using the OR rule. So false or true is true. This is going to turn out to be sort of false or false. That's the only time that an OR is false. So that'll be false. And then down here, we're going to have true or true, which is true. Here we're going to have true or false, which is true. So that's going to be the value of that. Here we're going to have false and false, which is false. This is going to be false and true, which is false. This is going to be true and false, which is false, and true and true, which is true. So we're using the AND rule there. And remember that ANDs are only true when they're both true. So that only happens at the bottom, because we have not false, which turns into trues, and so it's true there. Okay, the conclusion then here is going to be true, arrow, true. This is the arrow rule. The arrow rule is only false when it's true, arrow, false. So true, arrow, true is fine, but true, arrow, false is not fine, so that's going to be false. And then we're going to have false, arrow, true, which is true, and false, arrow, false, which is true. So here it is, completed truth table on in the boxes here. So that's what you need to sort of look at to see if we ever have a situation where the premises are all true, but the conclusion is false. And so it doesn't happen in line 1, it doesn't happen in line 2, neither in line 3 or 4. So it never happens. You never have all true premises and a false conclusion. And so what that means is this argument is valid. So that's always kind of tricky. So remember that if you find the row, that means the argument is invalid. But if you don't find the row, that means the argument is valid. All right, here's another example. Again, just 2 sentence letters, so only 4 possibilities. But calculating things can be a little tricky. So this is going to be not true, arrow, not true. Which, again, you do the negations first in these cases, so false, arrow, false, which is true. This is going to be false, arrow, true, which is true. This is going to be true, arrow, false, which is false. And this is going to be true, arrow, true, which is true. So that's kind of what that looks like. Not Q is pretty easy, just got to negate the Q column. So that's going to be false, true, false, true. And then not the case at P and Q. The P will get negated first. So ands are only true when they're both true, so that's going to happen down here in line 3. So not P will turn into true, so it'll be true and true, but everywhere else is going to be false. So there we have it, completed truth table, and here's a situation where, we do have all true premises and a false conclusion, so that means the argument is invalid. Again, bearing in mind that these are the premises and the thing on the right here is the conclusion. All right, one more, and then we'll make things a little bit more complicated by adding a letter. But here we've got a premise P, no logical connectives here, so that's easy. Another premise and a conclusion. So filling out this first premise is really easy because there's no logical connectives. So P is just P, right? You just look over here to the left and see what the value of P is, and you're good to go. Let's see, second premise is a little bit more complicated, so we have P or Q. So ORs are only false when they're both false. So we've got a negated P and a Q. So we're going to have false or true here, that's true. We're going to have false or false there, that's false. We're going to have false or true. Excuse me, we're going to have true or true, which is true. And then true or false, which is false, which is true, sorry. So true, false, true, true. Remember, OR is almost always true except for when they're both false. And then our conclusion is not Q, so we're going to have false, true, false, true, right? That's just the negation of Q. So, do we ever get true premises and a false conclusion? Yes, we do. So right here in line 1 it happens, and so that means the argument is invalid. Again, if you find that, this is a bad situation, this is a situation where the premises are true, but you still get a false conclusion, so that means the argument is invalid. All right, so the most difficult that we're going to get in terms of truth tables on the exam is going to be with sort of what we call an 8-line truth table, and that's what happens when you introduce sort of another letter. So each time you introduce another letter, you sort of double the number of rows. So the number of rows is equal to sort of 2 to the n, where n is the number of sentence letters. So if you have 2 sentence letters, that's 2 to the 2, which is 4. But 3 sentence letters is 2 to the 3. So that's 4 times 3. Which is 8, and if you add another one, then it's going to be 16, and another one will be 32, and then 64, and then 128, and so on and so forth. So for our purposes, though, we're not going to go sort of higher than 3 sentence letters. So no more than an 8-line truth table, and so what I'm going to sort of show you here is first of all how to kind of set up the truth table to make sure that you get all 8 possible combinations. So if you look here on the left, you'll see that there's kind of an algorithm that's going on for getting sort of all 8 possible combinations. So the P, you'll notice, is half true, half false, right? So it goes by 4s, right? 4 trues, 4 falses. And then the Q goes by 2s, right? So it's 2 trues, 2 falses, 2 trues, 2 falses. And then the R's go by 1s, 1 true, 1 false, 1 true, 1 false. So it keeps on getting halved. So you take 8 divided by half, that's 4. So P is 4 and 4. Divide that by half, it's 2, and you get the Q. Q's go by 2s, and then you divide that by half, you get 1. Excuse me, not divided by half, divided by 2, you get 1. And then you get true, false, true, false. So each time you divide everything by 2, or you split it in half, and you get the algorithm. So by 4s, and then by 2s, and then by 1s, that will get you all 8 possible combinations. So that means more calculations. It means the substitution stuff gets a little bit more tricky, but it's still the same idea. You just sort of fill out the truth table, and you check and see if you ever have true premises and a false conclusion. So I'm going to fill this out here. I'm going to start with the easiest sentence, which is the conclusion here, because it's just not P. And you'll see here in a minute that it actually makes sense to start with the easiest calculations. So not P is just going to be the opposite of our P column. So instead of true, 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 false, 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 we have false, 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 true, 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 true. Okay, so working backwards here, let's do not the case at R or Q. So here we have a situation where we have a parentheses. So we got to do our work inside the parentheses first and then negate it. So if whatever's in the parentheses turns out to be true, the final value will be false. If whatever's in the parentheses turns out to be false, then the final value will be true. But inside the parentheses is R and Q. So we need to look here. For instance, line 1 is going to be R, which is true, or Q, which is true. And then line 2 is going to be R, which is false, or Q, which is true, and so on and so forth. So inside the parentheses, we have this or, and the only time that it's going to end up being false is when both of those things are false. So when the R is false and when the Q is false, then inside the parentheses, it'll be false. Every other time inside the parentheses is going to be true. So what we'll get here is inside the parentheses, true, true, true in lines 1 through 3, false in lines 4, and then again, true, 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 false inside the parentheses. But you got to remember then, we still have that negation to deal with. So if it's true, 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 false, true, 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 false, then it gets sort of negated. It'll be false, 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 true, false, 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 true. So there we go. That's that column here. And then over here for the first premise, we have P arrow, Q, and R. The only time we'll have to do the parentheses first, but ultimately we'll be looking at sort of the arrow rule. So it'll be P arrow something. So the only time that that's going to turn out to be false is when the P is true and then what's inside the parentheses is false. So for instance, in line 1, that's not going to happen. It'll be true, arrow, true, which is good. So that'll be true, but line 2 is going to turn out to be true, arrow, false because of that and. So inside the parentheses, it'll be false. So true, arrow, false is false. And that happens again in line 3, in line 4. But then everywhere else it's false arrow something, so false arrow whatever is always true. So it looks like that. So here we are, we've got a filled out truth table now, and of course we're not finished until we check and see whether or not we ever have a row with all true premises and a false conclusion, right? So again, looking for true, true, false somewhere. And in this case, it never happens. In fact, we only ever get all true premises once, and when that happens, the conclusion is also true. So we never have a situation with all true premises and a false conclusion, so that argument is valid. So, same kind of deal as the 4-line truth table, is just a little bit more complicated. You still fill out the table and check and see whether or not you have a situation with all true premises and a false conclusion. All right. Another thing I want to talk about sort of is abbreviated truth table. So I mentioned sort of earlier that it makes sense to start with the sentences that are easiest to calculate. And the reason that I say that is because as you start filling in the truth table, you'll be able to sort of stop working on certain lines when sort of certain conditions are met. So remember that what we're looking for is a situation where you have all true premises and a false conclusion, right? We're looking for that that counter example that shows that the argument is invalid. So what you can infer then is that well, if I have a line that has a true conclusion, for instance, or a line that has a false premise, then I know sort of right away that that is not going to be the line where we have all true premises and a false conclusion, right? So all the premises need to be true and the conclusion needs to be false. So if we have a true conclusion or a false premise, we can ignore that particular line or eliminate it. So we have, as kind of a rule, or a way to sort of abbreviate our filling out of the truth table, this principle which says, eliminate any row with a false premise or a true conclusion. And if you end up eliminating all of them, well, that will mean your argument is invalid. And if you can't eliminate all of them, well, that means that that you're going to have a row with true premises and a false conclusion, right? So this is kind of the abbreviation. So again, I'll kind of show you how this works with an argument, but the idea is that we just sort of look for any row that, or excuse me, the idea is that we start with sort of the easiest to calculate, because that will help us sort of narrow things down a little bit so we're not doing sort of so many calculations. So here's an argument where the conclusion, again, conclusions are over here on the right. Here's an argument where the conclusion is really easy to calculate. The conclusion is just P. And so the column here is just going to be whatever P is, right? So true, in my case, true, 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 false, 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 false. Or maybe I said too many truths, but anyway, 4 truths, 4 falses. And so if I can eliminate any row with a true conclusion, that means I can eliminate all 4 of these rows, right? The first 4 rows, I just don't have to deal with anymore, and I can sort of move on to these other premises. So I can eliminate any row with a false, with a true conclusion, and also any row with a false premise. So let's do a premise and see if I get any false ones. So premise 2 here is an and ands are almost always false. They're only true under one condition, which is when they're both true. So the only time that that's going to happen is when my Q is true and my R is false. So that'll be down here in line 6, where Q is true and R is false, but R is negated, so it'll turn out to be true. So I'll have true and true, so the whole thing will be true. But everywhere else in these 4 lines, it'll be false. So false premise in 5, 6, and 8. So that eliminates all 3 of those rows. So I'm down to 1 row, right? There's only sort of 1 place that I could possibly have true premises and a false conclusion. And so I need to calculate the value of this 1 premise that's left, right? I went down from 8 to 1 for calculations in terms of the first premise. So first premise is P arrow not R. So that's going to be false arrow not false, which is false arrow true, which is true. So hey, there it is, right? True, true, false. I couldn't eliminate all of the rows here. I got down to 1, but that last one was the kicker, right? It had all true premises and a false conclusion. So that means this argument is invalid. So it's a way to make these things go a little bit more quickly. You don't need to fill out the sort of entire row. You can kind of just focus in on where the row might be, and this will save you some time. So it's not you don't have to do it this way, but if you want to do it this way, it's certainly an acceptable way to sort of do a truth table. Okay, so I'm going to end with a brief discussion about the shortcut method and why you might want to use it. So the shortcut method is sort of the shortest way to do this. Well, it's not. In this case, it's not even a truth table. But doing sort of calculations in order to figure out whether or not it's possible to have all true premises and a false conclusion. But the shortcut method is especially helpful if you start introducing sort of even more letters than just 3. So if you recall, we had an 8-line truth table. We went from 4 to 8 when we went from 2 letters to 3 letters. So if we go to sort of an argument that has sort of 4 letters in it, well, that's going to be a 16-line truth table, or an argument with 5 letters in it, that's going to be a 32-line truth table. So that's a lot of calculations for those kinds of arguments, and the shortcut method would help, or excuse me, the abbreviated method would help, but the shortcut method could go sort of even faster. And it does require sort of a certain amount of mastery of these calculations. You need to be able to kind of look at these things and do them quickly. But I just thought I would sort of demonstrate with a couple of arguments how this would go. So we're not going to make a table, we're just going to put up an argument here. So we've got a number of things going on here. So one thing to sort of mention is that here's an argument with 3 premises. So if we were doing a truth table, that would be even more calculations, and of course a conclusion though. So what we're looking for is a situation, if we can find it, we're looking for a situation where the premises are all true and the conclusion is false. And the other thing I'll sort of note here is that this argument has 5 sentence letters, right? We have P, Q, R, S, and T. So if we were to do a truth table with this, we would have 32 lines. So we have 4 sentences with 32 lines. That's 128 calculations that you would have to do if you were to completely sort of fill out the truth table. So nobody has that kind of time. So we're going to try the shortcut method. And the way that the shortcut method works is to try to come up with an assignment for all the letters, so P, Q, R, S, and T, that would get you all true premises and a false conclusion, right? We're just going to go see if we can do that. So I'm going to start with the conclusion here, because the conclusion is just R. And so the only way for that to be false is because this is the conclusion, we're trying to make it false, is for R to be false. So R has to be false in order for us to have a false conclusion. And again, that's what we're trying to see if this is possible. Can we get all true premises and a false conclusion? So that's the conclusion, and that's R. And one nice thing about that is if R is false, then with premise 3 over here, we're going to have false arrow something, right? It'll be either false arrow true or false arrow false. But either way, that's going to end up being true. Because the only times arrows are false is if it's true arrow false. So false arrow true, false arrow false is true with the arrow rules. So that's nice. So if we make R false, we make, not only do we make the conclusion false, but we make the premise 3 true. Well, let's keep going. So premise 2 is an and we're trying, and remember, this is the premise, so we're trying to make it true. So ands are only true under one condition, right? They're only true when both conjuncts are true. And so our conjuncts are Q and T, so that means Q has to be true, right? And T has to be true. Otherwise, that premise will be false. So that's kind of a bummer. that we're sort of narrowed down. Well, actually, that's kind of good that we're sort of narrowed down. But it's a bummer in the sense is that we're probably going to end up with an invalid argument here. So Q has to be true, T has to be true. Now all we need to do is make premise 1 true, right? We've made premise 3 true, we've made premise 2 true, we've made the conclusion false. Now all we need to do is pick an assignment for P and S that will get us a true premise. And in fact, there's 4 possibilities here, and we haven't narrowed ourselves down in any way, so we could just sort of pick whatever we want in order to make that premise true. So I'm going to just make P true and S true, and that'll get us true or false, which is true. So here's an assignment that gets you all true premises and a false conclusion. So that means the argument is invalid. So remember, if you can do this, that's bad, right? The all true premises and a false conclusion is not a good situation. All right, so we'll end here with one more shortcut example, and that'll be it for this video. But I wanted to do an example of one that is valid, just to show you what happens when you can't find this assignment and how you kind of know that it's impossible. So again, remember, we're shooting for all true premises and a false conclusion. Another situation where we have 3 premises, another situation where we have 5 sentence letters. So again, it would be, if we were doing a full calculated truth table, that would be, 32 lines and 4 calculations each, which is 128 calculations, which is a lot. So we're going to try to make an argument that has all true premises and a false conclusion. So premise, conclusion, true, false is what we're trying to do here. Okay, so looking at these premises, I see that my third premise is R, and so the only way to make that true is for R to be true, and that's going to affect my conclusion here, right? So if R is true and my conclusion needs to be false, that means T needs to be false, and so there's that. Now I'm in a situation where if I look at sort of premise 2, if I make it true, there's only one way to make premise 2 true, and that's by having P equal to true and Q equal to false, right? Because that will make not Q true. So now I have P true, Q false, R true, S we don't know yet, and T false. So that, so far so good, or at least it looks like we might have an invalid argument, right? So we've made these 2 premises true and made the conclusion false. So let's see if we can do anything about this first premise. So the first premise is P arrow, S, and T. So we know that P is true and T is false, and we don't know about S. But it looks like no matter what we do with S, we're going to end up with something false. So this is an and in parentheses, and in order for an and to be true, they both have to be true. So this T is already false, so that means this is going to be false. So no matter what we do with S, we're always going to get true arrow false, which is false. So that just means it can't happen, right? We can't get all true premises and a false conclusion. We didn't really have any options for anything else here, right? R had to be true, T had to be false, P had to be true, not Q had to be false in order to make these other guys true, the other premises true, and the conclusion false. So if they have to be true and false, or they have to have the assignment that they have, then there's no way to get all true premises and a false conclusion. So this argument is valid. It's just not possible. Now, there are other ways to show validity for these sort of complicated arguments, especially these arguments with a lot more than just sort of 3 letters, and that's the proof method. So what we're going to do after we're done talking about sort of truth tables is move on to proofs and show you how to prove that something is valid in a different way. So look forward to that in the next video.